Hello, guys. Nice to see you.
Hello.
Hi.
Hello.
Good afternoon.
Good afternoon.
How are you?
I'm fine, thank you. Doing well. How are you?
Doing well, thank you.
Mhm.
Good afternoon, Mr. Brus.
Hello, hello.
Mr. Brus.
Hi.
Hello.
Hi.
Good afternoon.
Welcome you to our discussion. So probably first question, did you manage to practice with long kappa? Does everything go good?
Yes.
Okay, yeah, practice with providing correct answers, and everything should be okay. Hello, hello, everyone who just joined us.
Mr. Brus.
Yes.
So we'll have to complete one long kappa for the week, or it's more than one.
Yeah, every week you will get this long kappa homework assignment with 10, 12 problems, and you will have time from Monday morning till Sunday evening to work on these problems and submit your answers.
Okay, thank you very much.
Yeah. Okay. Cool. Then I guess most of people who wanted, they already joined. The rest also welcomed on the way. So last discussion, we considered the one-dimensional motion with constant acceleration. So first of all, we define main parameters which are necessary to describe motion of a body, and that was specifically along one axis, and answer this main kinematics question means predict where body will be positioned in like at any moment of time. Yeah, hello, hello. So that means we introduce instantaneous velocity and acceleration, define what it is, and then we proceed with the derivation of equations which are like set of kinematic equations which are valid for motion along axis, like along straight line, and assuming that we have constant acceleration. So let us maybe refresh it. Where's my pen? So we derive the following equations. It is x, like position as a function of time, which is x naught initial position plus initial velocity times time plus constant acceleration times t squared over 2. So similar we can write for velocity.
I'm sorry, Professor, you're not sharing
Yes?
the screen.
Sure. Do you have any question?
I mean, you're not sharing the screen.
Oh, sorry. That is valid comment. I agree. Somehow I thought that it's already on. Oh, okay. Now it should be visible. Okay, thank you for letting me know. So the same we can write for the velocity as a function of time, v naught plus constant acceleration times t. And we also derive one more equation, which can be useful when we don't like eliminate time. So velocity square is equal 2v naught r square minus 2 constant acceleration a times x minus x naught. So these are equations which describe motion along straight line with constant acceleration. And that will be useful also for us in today's discussion on the way as we address motion along motion in 2 dimensions.
There should be plus, shouldn't be?
We
V0 squared plus 2a delta x.
1 second. Yeah, I think so. Let me double check. And again, you may not remember exact form of equation, but yeah, you are right, plus. But it can be easily derived when we express time from the second equation and substitute this expression of time in the first. So again, it's another thing that good to remember how you get to equations, and don't try to memorize equations itself so much, because that there's always chance to forget, but if you understand how you get them, that is always with you. So let us introduce motion in 2 dimensions. So now we have axis x and y, not like before we had some x and time t. Now we have 2 axes which are responsible for 2 dimensions. And in this 2-dimensional space, there is some path, like trajectory of moving body. Let's say we have some point A and some point B. So our body moves, we consider this motion from point A to point B. Obviously, since we have 2 dimensions, we need to deal now with vectors. And in order to define position of the body at any point, we introduce a so-called position vector, R vector. When it moves to point B, there will be some other position vector because body will be in different point of this 2-dimensional space. So how it will be defined? Here is, if we have a vector between 2 points A and B, so we can call this vector delta R. It's change of position vector, initial position vector. So according to rules of adding 2 vectors, we can write that the resultant position vector will be R plus delta R. So now, in order to proceed further, we also need to introduce main parameters which describe motion in 2-dimensional space with like taking into account this position vector. And obviously these parameters will be also vectors because we deal in 2 dimensions. So for instance, this average velocity will be already vector, and that will be delta R vector over delta T. But we know already that in order to describe motion of the body, at any and define its position at any point of time, we need to deal with instantaneous parameters, which are instantaneous velocity and acceleration. So instantaneous velocity will be limit delta t approaches to 0, delta r over delta t. And this is dr vector over dt, like derivative of position vector over time. So it is possible to take derivatives of vectors because from mathematical point of view, it's just something like we have some vector divided by some scalar. And the result of derivative of a vector will be also vector. In this case, derivative of position vector will give us velocity vector. Obviously, we need another parameter, which is instantaneous acceleration vector. This is limit delta t approaches to 0. Here is delta v vector over delta t. And this will be first derivative of the velocity vector over time. Or this will be second derivative of position vector over time, d squared r vector d t squared. Okay, with these definitions, we already know that position of our body is defined by position vector in two-dimensional space, and we also know how to use this position vector in order to, as a function of time, in order to get velocity vector and instantaneous velocity vector and instantaneous acceleration vector. So now let us consider some case of motion in two-dimensional space with constant acceleration. But keep in mind that all these parameters are vectors. And let us show how we address the same main question of kinematics. Means that in two-dimensional space, we actually want to know position vector as a function of time. So this is the main question we want to answer. So at any given moment of time, we want to know what will be position vector of our body, means define exactly position of our body in two-dimensional space. It could be also three-dimensional space, but the concept is the same, but it's just less of writing when we deal with two-dimensional space. So as we discussed earlier, we can split vector in different components. If we have two axes, it is convenient to split vector into components parallel to each of the perpendicular to each other axes. The same is also true when we consider motion in two dimensions. It is convenient to split position vector in two components and then consider motion in two-dimensional space as the synergy of like combination of motions along straight lines, like two motions which are independent from each other along two lines, two directions perpendicular to each other. So in our case, it's along axis X and along axis Y. So why? Because we already derive main equation, kinematic equations for motion along straight line. So we can apply them to each of these components of two-dimensional motion, and then just sum up the result in according to the rules of adding vectors, and we will eventually get the answer in vector form, how our position vector will be dependent on time in this two-dimensional space. If we have three-dimensional space, we can split this position vector in three components, but we will do it in two. So we have position vector we can write that it's x times I unit vector. So this is component along axis x, and y times j unit vector component along axis y. So we agreed at the beginning that acceleration is constant, means that components of this acceleration along axis x and y, they are also constant. Acceleration x is constant, and acceleration y is also constant. So now we know already how to deal with this, because we can define velocity along axis x as a function of time. It will be Vx naught, initial velocity component along axis x, plus acceleration ax times t. The same for velocity along axis y. It will be Vy naught plus ay times t. So we know this, and we can write now the general equation for the velocity vector in this case of two-dimensional motion with constant acceleration. So v vector as a function of time is equal to the sum of two components of this velocity along axis x and along axis y. So means we will have Vx naught plus ax times t, and this times unit vector I. So we define direction along axis x. Then we have plus Vy naught plus ay times t, all these times j unit vector. So if we reorganize this a bit and group terms according to their type, so velocity plus velocity and acceleration plus acceleration, so this will look like this. It will be Vx naught times I unit vector plus Vy naught times j unit vector plus ax times I unit vector plus ay times j unit vector, and this all times t. So here we have two components. This is our initial velocity vector, v naught vector, and this is our constant acceleration vector, a vector. So eventually we have the following: our velocity vector as a function of time in this two dimension is initial velocity vector plus constant acceleration vector times t. And graphically, we can represent it as follows, maybe here. So we have some initial velocity vector, and here component of the change of this velocity because of acceleration. It will be a vector times t. So the resultant is the sum of these two components. It's v velocity vector as a function of time. Okay, with velocity, we made it already, we clarified. But in order to answer the main kinematic question, we need also to do the same with position vector. So now position along, since we analyze two-dimensional motion as the sum of two motions along straight lines along axis X and Y, we need to deal with the position as a function of time along axis X and along axis Y separately. So for this purpose, we can write that position along axis X as a function of time will be x naught, the initial position along axis X, plus v x naught t, initial velocity along axis X times time, plus acceleration a, constant acceleration ax times t squared divided by 2. So we know this equation because we previously derived it for this particular case, motion along a straight line with constant acceleration. So for y, for axis position along axis y, we can write the same. Y naught plus vy naught t times t plus ay times t squared divided by 2. Okay, now we have these two components of the position along axis x and y, and obviously in order to set to define the position vector r vector as a function of time, we need to add these two components in the as vectors. So we have x naught plus v x plus v x naught times t plus ax t squared divided by 2 times I unit vector, because this is displacement along axis X plus like position along axis X, initial position plus displacement because of initial velocity and constant acceleration. And then it will be the same for axis Y, y naught plus v y naught times t plus a y times t squared divided by 2. And this is multiplied by j unit vector. So if we rearrange and group the same types as we did before, the terms with this, of the same time, like position, velocity, and acceleration, then we will get x naught times I, no, it's j, times I unit vector plus y naught times j unit vector plus now the velocity component vx naught times I unit vector plus vy naught times j vector. This all times t, and plus the acceleration component will be ax times I plus ay times j, and all these times t squared divided by 2. So eventually we also get expression for r naught vector, so initial position vector, plus v naught vector times t, and plus this constant acceleration vector times t squared divided by 2. So we have shown how we can split motion to the remove that. How we can split two-dimensional motion in two components and quantify the position of the body in the scope of the model derived for motion along a straight line for each axis, and then in a vector form add these components and get final expressions for the position vector as a function of time for two-dimensional motion with constant acceleration. So at this point, it is good to consider some classical example of such two-dimensional motion with constant acceleration, and that is so-called projectile motion, or motion of a body thrown at some angle to the horizon. So we have two-dimensional space, x, y, and the trajectory of this projectile. So it will be some curved line which originates at the ground and then ends on the ground. It reaches some maximum point. Let's call it point A. Here is point B. So point A, it corresponds to the highest position of the trajectory at height h from the ground, and point B defines distance between the initial point and final point of this trajectory, and this is also as horizontal range. So obviously we have some initial velocity, some angle theta naught, initial angle at which this velocity is oriented. And in order to develop some model, quantitative model for describing this projectile motion, we need to consider some conditions which should be valid, and based on that we will proceed first. So first is the acceleration is free falling acceleration g, and it is always a line downwards, so only along axis y. There is 0 x component of this acceleration, and its value is not changing. So means that the maximum height and gravitation and this horizontal range, they should be much smaller than the radius of planet Earth. If we consider our planet as a location for this experiment, because otherwise, because of curvature of the Earth and also because of changing the value of the acceleration, free fall acceleration with the height, these conditions will not be valid anymore. So we need to specify that this maximum height and horizontal range, they are much smaller than the radius of planet Earth. Another important factor which should be taken into account is negligible air resistance. So we assume that this body has some, it doesn't move with very high speed and has good aerodynamical shape, which results in negligibly small air resistance in comparison to other factors, and that does not influence on the motion of this body. So in this case, when we satisfy these two conditions, we can proceed further. And of course, we want to split this initial velocity into two components. First component along axis x, let's call it Vx, not initial velocity component along axis x, and along axis y will be Vy naught. So since we know the initial velocity vector and its orientation with respect to the horizon, with this angle theta naught, we can write that Vx naught is equal to V naught times cosinus theta naught, and Vy naught is equal to V naught times sinus theta naught. So these are components, x and y components of the initial velocity. And we need to clarify how these components will depend on time. How they will change with time. So for instance, Vx along axis x will be, since we don't consider any air resistance and the projection of our acceleration, like g vector on axis x is 0, there will be no reasons to change velocity along axis x. So means that it will be Vx naught and it will stay constant. It will be different for velocity along axis y. So Vy is equal to Vy naught plus some acceleration a y times t. And this acceleration is our g, and we know that it at any point of this trajectory will be oriented downwards. So means that a y is equal to minus g. So we can write that this will be Vy naught minus g times t. So with this in mind, when we define time dependence of velocity vector component along axis x and y, we need to proceed further with the analysis of this trajectory. So, but maybe before that, we can highlight, for instance, and we need to understand that in the highest point, like this point B, there will be only component of velocity which is aligned along axis x. So it will be Vx. Because y component will be equal to 0. So it will reach the maximum point. It will be 0 velocity along axis y. It was before point A, before reaching this point A, the velocity along axis y was positive because it was moving upwards. And after this point A, the velocity along axis y will become negative because this body will just fall down. And that will be in the direction opposite to the axis y. So taking this into account, we can claim that at this point A, velocity along axis y is equal to 0. So Vy at some time Ta, Ta means time when this body will reach the highest point of this trajectory, means point A, is equal to 0. And y, like position along axis y at this time Ta, will be equal to h, which is the highest point of the trajectory, the height of this trajectory. So our goal is to quantify this age. So we can just substitute let us define this time TA, that is the starting point. So we know that velocity along axis y is changing with time as vy naught minus g times t. And this velocity will be equal to 0 when t is ta. Then from here we can express that this ta is equal to vy naught divided by g. And we know that vy naught is component of the initial velocity, and that will be v naught times sinus theta naught divided by g. So this is expression for time ta when our body will reach the highest point of its trajectory. This projectile will reach its highest point in the path. So now we can deal with this TA, substitute it in the equation which describes motion along axis y, and determine what will be the maximum height h. So let us do it here. So we can write that position y at time ta is equal to some initial position r y naught plus v y naught times ta minus g ta square divided by 2. Since we have just a sketch here to remind, we have the condition when our initial point is aligned with the origin of the coordinate, then we can write that initial position along axis y is equal to 0. So we just don't take this into account. And we need to write now, substitute in this equation expression for vy naught and ta. And here also this ta. So let us do it. So y at point ta is equal to h, and this is equal to v naught times sinus theta naught. This stands for the y component of initial velocity times ta, and ta we have shown on the previous slide that it is equal to v naught sinus theta naught divided by g. So minus g times divided by 2 times ta squared. So it will be v naught sinus theta naught divided by g, and this is squared. So if we open parentheses now and take into account that we cancel out this g in the numerator and have just g in the denominator, we will have the following. It will be v naught square times sinus square theta naught divided by g minus 1/2 times v naught square sinus square theta naught divided by g. So actually we get the second term is 1/2 of the first term. And that's why for the maximum height of our trajectory, we will get the following expression. It will be v naught squared times sinus squared theta naught divided by 2g. So this is the answer to our first question. What will be the maximum height of this trajectory h? And now, obviously, there is one more question to answer. That is horizontal range. What will be horizontal range? So again, we have point A and point B. So if it takes us, takes this body to move from ground level to maximum height of the trajectory with some time ta, then it will take the same amount of time for this body to fall down from point A back to the ground. So it will be another ta. So tb, time which takes for the projectile to go through all its trajectory and reach point B, will be 2 times ta. And we know expression for ta. So it will be 2 times v naught sinus theta naught divided by g. So now we have this time, and it is very easy to calculate the horizontal range. We know, we already discussed this previously, that component of velocity along axis x is constant, and it is equal to vx naught, initial component of the, x component of the initial velocity, constant. So what we need to do in order to get the horizontal range, we need to multiply this constant vx naught component by time tb, vx naught times tb. And now let us substitute expressions for vx naught and time tb. So this will be v naught times cosinus theta naught multiply tb. We just wrote down the expression for tb as 2 multiplies ta. So it's 2 multiply v naught sinus theta naught divided by g. So this will be equal to 2 times v naught square sinus theta naught times cosinus theta naught and divided by g. So taking into account the trigonometric identity that sinus theta times cosinus theta is equal to sinus 2 theta, we can simplify this equation and get the final form, which will be 2.
I'm sorry, I guess you forgot the coefficient before sine and
Yes.
cosine.
There should be 2 sine theta cosine theta, right? In order to be sine to.
Yeah. So it should be here too. You're right. 2 sine theta times cosine theta is equal to sinus 2 theta. Yeah. Okay. Sure. So our final equation, then of course this 2 will not be here. It will be v naught square times sinus 2 theta and is divided by G. So now we have this final equation, and let us just consider the maximum horizontal range. What will be the maximum horizontal range based on this equation? Any ideas?
V0 squared over G.
Exactly. V0 square over G, because sinus 2 theta, its maximum value will be unity. And that will be true when we have 2 theta equals to 90 degrees and theta, like not initial angle at which this projectile is starts its motion, will be 45 degrees. So means that we will reach the longest horizontal range when this initial angle of the initial velocity vector orientation with respect to horizon will be at 45 degrees. So this is everything what we had to consider and discuss during this lecture. So we introduced the main parameters for two-dimensional motion, which is instantaneous velocity vector, instantaneous acceleration vector. We have shown that it is convenient and easy to work with two-dimensional motion when we split all these position vector, velocity, and acceleration vectors along two axes of coordinates and deal with these components as motion along straight lines. So then we can apply already known mathematical models for this motion, assuming that acceleration is constant, do all calculations, then add up these components in the vector form, and eventually get the time-dependent position vector of this body moving in two-dimensional space. And that is automatically answering the main question of kinematics, because we can define position in two-dimensional space at any given moment of time. And as an example of some specific case of two-dimensional motion, we consider this projectile motion. What is special about this? That constant acceleration is not doesn't have two components, because projection of vector G of this acceleration, free fall acceleration on axis X is equal to 0. So it's aligned downwards parallel to the axis Y at each point of the projectile path. So this condition should be taken into account. And based on this, we could derive also equations for the maximum height of the projectile trajectory and define the horizontal range. So distance from the starting to the end point of this projectile motion. So with this, I would like to finish our discussion today. If you have any questions, you're welcome. Please don't forget to practice with long kappa and answer your submit your answers to long kappa so you feel comfortably. Yeah. If you have any questions, you're welcome to unmute you and ask. Don't need to raise hands.
Okay. Hi. Thank you for the. And I wanted to ask if it is enough to watch just the video from MIT, and if we understand it all, is it okay just not to watch the others?
That's up to you totally, what you feel. So first of all, what I have to say that the main source of information is textbook. That's with what you have to work. because all videos it's great, but it definitely will not give such in-depth explanation of physics concepts as it's given in the textbook. That's why, again, textbook is #1 source, and then on top of that, you can add whatever you want, any of these videos, or maybe some other videos which you can find in internet. So there is another question about grading of long kappa homework assignment, and there is also an answer quite efficiently. No, it will not be graded for this week, and starting from week #3, you will get homework assignments which will be graded, and that will contribute in total like about 20% to your final grade. So please be aware of this and submit in time. Don't break the deadlines, because then long kappa will not accept your answers. Okay, thank you very much for attention. It was nice to see you guys. Hope to see you on Friday. Take care and have a good day. Bye-bye.
Thank you.
Have a
Thank
great
you
day.
very much.
Thank you. Goodbye.
Bye.
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 Thank you. Goodbye.
Bye-bye.
Bye.